Good morning, good afternoon, and good evening to all our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Exaptive for sponsoring today's event. We're honored to have Exaptive as sponsor and today's supporter of the Data Science Central community. I'd also like to take this opportunity to mention and show our appreciation for some of the other recent sponsors, including Tableau, Microsoft, Hortonworks, Oracle, IBM, and Teradata, to name just a few. Past webinars are available on demand at datasciencecentral.com. If you haven't had an opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled Analyzing Census Time Series Data with Feature Extraction and Clustering. Before we begin, I'd like to briefly review the format of today's webinar. Today's event will be an hour long. We have one panelist, and I'll introduce him in just a minute. There will be 10 to 15 minutes of Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com in the next few days following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. I'm very pleased to introduce today's speaker, Matt Coatney of Exaptive. Matt's an artificial intelligence expert, data scientist, entrepreneur, technology executive, author, and speaker. For the last 15 years, he's brought advanced technologies to market, including chemical mining software LeadScope, legal text analysis products, and a predictive modeling tool for the U.S. Air Force. He now leads Exaptive's consulting team. Matt has co-authored a chapter of the book Data Mining, Next Generation Challenges and Future Directions, published by the Association for the Advancement of Artificial Intelligence and MIT Press. He's a frequent blogger and speaker, including TEDx, the International Legal Technology Association Annual Conference, and the Chief Information and Technology Officers Forum. Thanks for being with us today, Matt. We're looking forward to your presentation. In today's Data Science Central webinar, Matt will discuss feature extraction and clustering of time series data using city census data about businesses as raw material. He'll explain his approach for symbolically representing time series data with Symbolic Aggregate approXimation, SAX, and sorting them with Fourier transform. He'll also explain how algorithms from genetics can aid in clustering time series data, and you'll see the Python that he wrote to implement the algorithms. He'll also explore the results of the clustering with visual applications to find patterns in the census data. So Matt, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Great. Thank you very much, Bill, and thanks everybody for being here today. So let's go ahead and jump right in. I want to walk through what we'll cover today. So start with a little bit about a background about the project, sort of where it came from and the problem statement. And then we'll jump into an overview of the approach. Before we dive deeper into methodology, though, I'll give you all a preview of the results, sort of the teaser before we jump in. And then we'll walk through the various steps that we took to arrive at those results. And then at the end, we'll do a deeper dive and walk through those results. All right. So let's go ahead and start with the project origins. And it's worth noting the term Exaptive and where it came from, because it plays into this story here. So Exaptive is not a made-up term, not a made-up company name. It's actually based in biology. So the term exaptation refers to a feature that evolved for one purpose, but then got co-opted or borrowed for an entirely different purpose. And the classic example of that is a bird feather, where it was originally evolved not for flight, but for insulation, for keeping birds warm. And they discovered through various generations that it was really handy for flying. So that's sort of at the core of this project, because the essence of what we'll talk about today actually started 15 years ago in a very different industry. So I started my career as a biochemist. I have degrees in biochemistry and computer science, and one of the first projects in the companies that I worked with out of school, we were looking at protein and DNA and RNA sequence data. And we were developing algorithms, and this was 15 or so years ago, to cluster things like protein sequences or pharmaceutical drug compounds back in the early days of some of the data mining. So fast forward now to last year, where we were doing a project with a global health organization and looking at whether we could group countries together by similarity, so we could, say, find an intervention that worked in one country and apply it to another country. And very early in that project, I thought this technique that we used many years ago on protein data actually would apply with countries. We're trying to do the similar thing of grouping items together. And that leads us to today's topic. So as we were working with international country data, we stopped and thought, what other time series data out there, what other metrics about entities would be interesting to explore? What kind of questions can we answer? And that's when we thought about U.S. cities, so bringing it a little bit sort of closer to home. And the real challenge, the real goal here is, can we determine which cities are similar? That seems like a pretty straightforward question until you think about all the different ways that you can compare cities. But if you can answer that question, if you can determine which cities are similar, you can do all sorts of things, from social good activities like identifying a social program and intervention in one city that worked and apply it to a similar city. You can use it for business decisions, like where am I going to move? What kind of jobs should I be looking for? What's the best real estate to buy? And then the quintessential question, which we'll dive into a little bit later, is sort of what's the next Silicon Valley? Where is innovation happening? All right. So you all are data scientists or have been in the data science community long enough to know that with many projects, there's not one single algorithm, one black box step you take, you press a button, and voila, the results come out the other end. This is no exception. So we have a number of steps that we take to both prepare the data and then extract varying orders or degrees of features out of that data to make sense of it. And we'll talk through that. So we'll start by talking through how we gathered the data, where we obtained it from, how we prepared it using the Python scripts. Then we'll talk about extracting features at a couple different levels, both for individual time series metrics and then at a more aggregate level for cities. And then we'll wrap up by visualizing those results and then also talking about how you can adjust weights and influence the outcome of the algorithms. All right, so before we jump into methodology in more detail, I'd like to do a quick screen share of an application. So this was something that we built with the Exaptive platform, basically to visualize the results. And so I'll give you a quick teaser here. The results here on the left-hand side, these are the clusters. So each city is represented by a dot, and the centroid of each cluster is here. And then on the right-hand side are a number of parameters where we can tune the algorithms. We can adjust the cluster size or the types of cities or the population we want to include in our algorithms. And then we'll talk later on about how we can adjust weights to influence how the algorithm groups these countries. We can also change how the nodes are sized. So this is the default clustering, sort of the default settings that come out. It's 6 clusters looking at countries between 1 million and 20 million, with everything weighted equally. And you can see sort of the large cluster up here of large cities in New York and San Francisco and DC and Boston. LA is in a different cluster over here, Chicago's over here, and you can see how they break out. We'll walk through all these results in more detail after we walk through some of the approach. All right. So let's go ahead and talk about where this data came from. So At the beginning, Bill mentioned that we looked at U.S. Census data about businesses, and that is partially true. We actually extended our data set a little bit, and I'll explore the reasons why we did that in a moment. But in effect, we looked at 917, to be precise, metropolitan areas. These are groups of cities that belong in a metro area. So if you think of New York, that's actually New York and some of the suburbs around the major city. And that seemed to be an appropriate level to analyze rather than going more granular like at the zip code level or going more macro at the county or state level. In all, we looked at 60 time series metrics, and I'll talk about the sources of those now. So the Census Bureau has a wonderful site. There's lots of data out there, but finding it, getting it down, and processing it can be a challenge. So as of yet, there's no easy way with the Census Bureau to just pull all that data down in a common relational format and run with it. You have to do a fair amount of massaging. The files were produced at different times for different needs, and that proved to be a challenge, which we'll talk through a bit. They do have a newer API that's available, though, so for future work, we hope to be able to plug into that and standardize some of this approach. Now, we looked at predominantly county business patterns. So this is, provide a link here, and it's basically information about the number of businesses and the payroll for those businesses by the metropolitan area and industry using a standard code called the NAICS code. And we extracted 17 high-level industries and for data ranging from 97 to 2013. Now, the reason we extended it a little bit is we wanted to give a more holistic view of what a city is than just looking at its business. So we looked at a complementary data set called the Census Data Books. These are extracts from the most recent full census in 2010. And it ranges from things like demographics, age and race demographics, health, education, labor, and so on. And that metric was a little more constrained. It had either a few years of data or a range of about 8 years. Now, the last piece that we wanted to bring in had to do with crime data. And while the census does have some tracking and reporting on crime, we wanted to go straight to the source. And in the US, there's no better source for crime data than the FBI. So we turned to them for 4 metrics in particular, looking at both violent and nonviolent crime of murder, robbery, assault, and burglary from 97 to 2010. And I recommend if you're looking at crime data, this is a great place to go. They have a program called the Uniform Crime Reporting, or UCR program, where you can get a lot of this data out in a variety of different forms. Now, data gathering aside, that was just the first step. The challenge in many of these projects is getting the data in a format that you can actually use, that you can send to all these different algorithms that people have developed over the years. And so the old saying about managing software development is like herding cats. I've been a software developer, so I can appreciate this. The same is true for data projects. And so, so it is here. So we won't spend too much time talking about the preparation side, but it's worth noting a couple of things here. It's, as with many projects that you all have probably worked on, that upfront massaging of the data actually accounted for the majority of the effort. So it took about 8 hours or so of coding, about 330 lines of Python in all. And we were doing things like getting the files into a format we needed, so using either VBScript or a Python library like OpenPyXL to pull that into a CSV or to an internal format. Every data file that we received, even from the same source or for the same metric, often had different names for those metro areas depending on when the data was produced. So we had to do a fair amount of normalization to clean up and sort of join the data across those names. And then do a fair amount of the usual stuff like mapping names, applying business rules, and sort of the goal, the end state, was to get the data in a JSON format that we could then work with sort of universally across all these different algorithms. We promised some Python code, so this is our first look at that. I collapsed down the methods up above so it was a little more readable, but basically this is the data preparation code that we wrote. And it talks about getting information about the cities and the industries, formatting the city names, and then populating the different types of data, the county business data, data book data, and crime data. And if you can see on your screen down here towards the bottom, that's where we actually use a library, just import JSON, and then it's JSON.dumps data. We'll write the data out to a file or to a string. You can read that in later using JSON.loads. Okay. It's worth noting, and I'll show a slide here, where the resulting structure is important because it will help understand what the algorithms are doing a little later on. Effectively, every city, we'll call an instance here, every city has, in this case, 60 metrics or 60 observations associated with it. And each of those observations has a series of time stamp values, in this case, annual data, for each of those 60 metrics. So it's a complex data set. It's hierarchical, where it's nested down. But then for each of those observations, there's a timestamp, which you see on the left-hand side, that corresponds to what year that data came from. So in this example, those are the timestamps on the left, the years that accommodation and food services data was available. And then on the right-hand side, those are the actual values for Albany, New York. And you'll note some missing values in the first few rows there, which we will address as we talk through the algorithm. Okay. So we've downloaded data from Census Bureau and from the FBI. We've gotten into a format that we're now ready to work with it, and here comes just the fun stuff, the algorithms. So we'll start by looking at feature extraction, and this is a point worth sort of pausing and noting that extracting meaningful features, the signal from the noise, is one of the most critical steps of most of the projects that I've been involved in from sort of the machine learning and artificial intelligence space. Whether it's extracting low-level features from images for image classification or for robotics, time series data here, audio data for doing things like music recommendation engines, getting the right features out to then work with are critical. And if you think about it from a sort of a biological sense, our brains are about the best pattern matching machines out there. But they would not be able to do all the amazing things they can do without the facilities that we have in our visual cortex, in our ears, in our sensory apparatus that takes those raw signals coming in from our environment and actually turning them into meaningful features that we can then recognize patterns from. So the same goes with these algorithms here. So how can we go from this sort of messy time series data that's all over the place to something that we can actually work with, compare, and contrast? Okay. That brings us to our first core algorithm, and that's called the Symbolic Aggregation, approXimation, or SAX. And the goal here is we want to distill down for a time series a feature that preserves both its structure, so the shape of the curve, as well as its scale. Is it significant? Is it low? In between. Now this algorithm, the SAX algorithm, was invented in 2002, about 14 years old now, down at UC Riverside. If you go to their website, they have a picture of Lisa Simpson playing the saxophone, which I love that sense of humor. What it does is it takes each time series and it encodes it as a string. And it's basically letters from A to T. And the height, or that number, or the letter, as it goes from A to T, represents sort of smaller to higher transitions in the curve. And then we extend this algorithm a bit by adding in the average frequency to get a better sense of scale. Now, it's worth noting here why we chose this particular algorithm. So, and that's one of the conundrums in data science. There's so many different feature extractions, whether you're looking at images or time series data or anything else. There's lots of different ways to extract features, so the choice is important. There are a class of algorithms of which SAX falls into, where this Fourier transform, the Wavell transform, and then this, that effectively capture scale and structure of the overall curve. And that's suitable for time series data where the general trend is either up, down, or flat. There's not a lot of cyclical, seasonal kind of behavior there. So you don't really need that frequency, that cyclical element to be pulled out as a feature. If you do need that with the time series data that you're looking at, there are other algorithms that you can look at from the signal processing and audio space that handle that, because frequency in sort of the cyclical wave form is important in those scenarios. But for us, we don't have that, so the SAX algorithm is a good choice. In the literature, when compared up with Fourier and others, it performs from an accuracy perspective as well, but it has the added benefit of being faster and more compact. The other advantage for me personally is, as a bioinformaticist, this smells an awful lot like those old DNA and protein sequences I used to work with. So there's both a comfort level, but also an ability to take off-the-shelf algorithms that work in the bioinformatics space and apply them here. And that's what we'll talk about next. Okay. So another quick snippet of code. So we leveraged a library from Nathan Hoffman out on GitHub. It's an implementation of SAX in Python. We chose to do that rather than write our own because it's a relatively straightforward algorithm, but it's a problem that had already been solved. The code here basically walks through each instance and each observation in that instance, so each metric, and it takes the time series graph and converts it to a string with an average frequency. And we do some handling for missing values basically by substituting a dash, which we can use later in distance calculations, and then also ignoring those in the average. All right, so we've gotten our data in, we've gotten in a good format, we've extracted now these SAX features, these strings. But in order to actually have them be useful, we need some way of comparing them. And that's where a distance metric or a similarity metric comes into play. Again, borrowing from the bioinformatics space, where there's a lot of work in sequence alignment and comparison, is there's a concept called, an algorithm called the Levenshtein distance. The H is in the correct place. I had to look that up multiple times. But this is a distance metric I've used for the last 10 or 15 years to compare two strings. And the benefit of it, in addition to being a proper mathematical distance function, is that it does provide for some fluidity in the strings it's comparing. So it handles inserts and deletes and substitutions. And when you're looking at time series data, that's important because there could be a phase shift. Let's say we're looking at city data. We're looking at an IT boom that happened, let's say, in 2003 in one city and 2005 in another, but otherwise the boom looked the same. If you just try to naively match those two time series together, that phase shift will basically make your distance significantly different. The Levenshtein distance handles that for you, that variability, and effectively sort of grades it as partial credit. They're close. So that works well in bioinformatics. We found, working with country data for the Global Health Initiative, that it applies just as well to this kind of demographic time series data. Okay. So at this point, we've extracted what I'll call sort of first order raw features. So if you think about how, again, the visual cortex or how we do image processing as people, the first order of feature extraction is getting all the edges, and it's getting the shade, and it's getting sort of where's an angle, where's a straight line. It's finding those gradations. But then you can extract another level of features from that, and that's what we're doing here with this fingerprinting. We're basically taking some very complex list of features, and we want to reduce it to a higher order feature. And this is alternately known as a feature vector. This is a little bit complicated to understand, so I'll sort of walk through it. Once you get it and intuitively makes sense, it's a really useful feature. So effectively, if you have a bunch of strings for each of these different metrics, what we do is we cluster each city just on one feature. So we'll pick IT jobs again, which we mentioned before. What we do is we cluster all of the cities just on that one feature, and we assign a class, basically the cluster ID, just for that. So we now have, for 3 different cities, we have classes. or however many cities we have classes for that feature. And then we just repeat that process. So in this instance, it's 60 features, 60 metrics we're dealing with. So we have a feature vector that's 60 characters long, where each character represents one of those features. And this is very helpful reducing high dimensionality data down to something that's both more manageable and more meaningful. It's again, it's sort of taking some of the signal from the noise. We did this for countries where we were looking over 500 different metrics. And the bioinformatics work that we did when we were looking at drug compounds, we were dealing with feature vectors that were 37,000 characters long. So this is a very extensible, very scalable kind of approach. All right. So as I mentioned, it lets us go from this very sort of abstract, very detailed view where we've got some features that we've extracted from the time series and gives us this to the bottom where we've got a feature vector. So we've got numbers that correspond to the class for that particular feature, and you can quickly see visually which cities, which features line up. And that ability to sort of visually scan quickly and see the relationship is exactly the same benefit that we get when we look at these feature vectors for clustering cities. All right. So here's a bit of the code. So a couple of notes on this. We decided to implement a custom clustering algorithm. It's not a custom clustering algorithm, but we wrote custom code for it because we wanted to include our custom distance metric. You can use scikit-learn in some of their algorithms, like K-medoids will let you insert your own distance matrix. Others, though, like k-means, won't let you do that. So really a design preference. You can either roll your own or go out and modify what's already out there. We did use a Python extension that is out there for the Levenstein calculation, which is nice, so you don't need to rewrite that one. And then we do various things for assigning the points to clusters and such. Okay. So we've come a long way. So we've taken our time series data. We've extracted those features out using the SAX algorithm. We've compared them using the Levenstein distance, which then gives us our fingerprint feature vectors. We've got one more step. So now we're ready to cluster, which just seems like where we should have started from. So a lot of work to get to this point. We need one more piece, and that's another way to compare these feature vectors. And there are a variety of algorithms that are out there. The one calculation I've been fond for over the years is called the Tanimoto coefficient. Again, borrowing from comparing, say, two feature vectors from gene sequences together. And you can see here in the little snippet of code that basically what it's doing is it's looking across the string, and everywhere that it has a same class or the bit is on, in the case of the traditional definition, then it gets awarded a point. If they're different, it does not. And then you calculate sort of the overall distance from that, or similarity, depending on which one you're interested in. Okay. And this is an important point to note because we tend to jump in with clustering and present the results and say, here they are. And with clustering, you don't really know whether the clusters you find are statistically valid or whether they are interesting or whether you're sort of left guessing because there's the whole point of clustering. It's unsupervised. So like classification, you have the answers to the test. You can run a training set through. You really don't have that with clustering. So you need a different metric. And there are a variety of these out there. The silhouette coefficient for the type of data we've been working with seem to be a good measure. And it basically tells you what the overall quality of the clusters that an algorithm produces. It looks at each instance in a cluster and compares it to the distances within that cluster versus distances to all the other members of other clusters, and basically says, does this point belong in this cluster or not? It ranges from -1, which is really, really bad, up to 1, which is ideal. Real data being what it is, you usually see good results hovering in the 0.2 to 0.5 range, depending on the data. But this gives you a sense effectively to know, one, do you have decent clusters? And then as you make changes to your algorithms or you tweak metrics and things like that, are you getting better or worse? All right, So that leads us now to actually walking through some examples, which is my favorite part, getting to see the results. So I'm going to go ahead and share my screen again. Okay. So this screen now hopefully makes a little more sense that we've talked through the approach. Over here on the left, we have our clusters. So each connected cluster is one cluster, and the centroid is here in the middle. Some of the labels appear as we zoom in to a particular one. You can see all of the labels, for instance. Over on the right-hand side are our parameters. So we can right now determine or fix how many clusters we want. That can also, we've had versions of this in the past that will let you auto-detect what cluster size is the best based on that silhouette coefficient. But right now we just leave it as a lever that you can move. And we can come over here and change the filtering threshold for which cities we're interested in. And then we can adjust the metrics here. Now you may say there's only 6 filters here and we've got 60 metrics. Tuning each individual metric is both tedious and not necessarily the most use of your time. So we grouped the metrics into these categories of crime, demographics, business, and so on. So you can come in here and adjust it. Every feature in that feature vector has an initial weight of 1. And basically what you can do is you can adjust the scale of that feature so that it's more important. So if 2 cities have the same class, the same item for that feature in the feature vector, it actually gets weighted as more similar than if other features were compared the same. So it gives you a way to sort of influence the results and guide the clustering to what you're most interested in for a use case. We can also then change the size and the color of the nodes. So right now we've got it where the size of the node is just population, so makes sense, Los Angeles, by far the largest. Riverside in the middle, Orlando, Phoenix, and so forth. And the shading right now, we just picked health, sort of healthcare, the number of physicians per capita. Okay. So let's go ahead and walk through some of those questions that we asked at the beginning about what kinds of things can you answer if you know what cities are similar. And the first one we'll look at is an example around crime and demographics, and specifically race riots. And so I'm Dayton, Ohio native. I still live here. And I remember not too long ago, and this was before Baltimore and before Ferguson, we had a race riot down in Cincinnati. And I still remember, the imagery from that and the pain that the people that were involved in was inflicted on. It was just a devastating event on all sides. And that was years before then, more recent instances of Baltimore and Ferguson. So the question is, can we from this data determine which cities look like those where they've already happened? And most importantly, it's not just for an academic interest, but it's can we find, were there interventions in some of those cities that worked, that reduced tension, that brought the community closer together, that we can then apply to these other cities that might be at risk? And so to do that, what we're going to do is look predominantly at crime and demographics. And we're going to weight lower down here the business, education, and others. So predominantly we want to cluster just on those metrics. If we click Apply Changes, pull it up, here we go. So we get a new set of clusters. Some are more dense than others. And before we look at the clusters themselves, let's go ahead and change what we're coloring and sizing these by. So let's size it by one particular kind of crime. Let's choose assault. And then we'll change the color to be unemployment level. Now, there's a few clusters in general. The ones up here are some of our larger cities, and it's what you would expect. But there's 2 clusters down here that are very interesting. So one includes Baltimore. The other includes Cincinnati. And you can see the related cities. And they tend to make intuitive sense. So from a Cincinnati perspective, Louisville is just right down the river from there. Very similar city. Detroit And you can see Detroit being very large in terms both of crime and then a deep blue, meaning high unemployment, as you would expect. So when we're looking at crime, and then demographics is not just along race data from the census, but it's also age data, the makeup of the city. And what we see is this clear cluster forming with Cincinnati, Detroit, Louisville, St. Louis, and others. And then Baltimore up here, a different cluster with Kansas City, New Orleans, and Richmond. And when you look at these, they tend to make intuitive sense. So that's helping with the validation. And I should have mentioned earlier that when we look at silhouette coefficients for these types of clusters, they tend to hover in the 0.2 to 0.4 range. So they're around where we would expect them to be for this kind of data. Okay. So a person could use a tool like this to help elucidate what the relationships are between cities for this kind of use case, and then perhaps look at, if you are a city administrator in Louisville and you're looking for ways to bring your community closer together, you now have a peer group that you could go out and seek what kind of techniques have worked there based on a similar background, sort of a similar genetic makeup for your city. All right. So let's go ahead and end on that quintessential question of what the next Silicon Valley is. I will make no predictions here. We'll simply explore the data and let it tell us what it does. So we're going to get a little bit more fine grained. We're going to go to 8 clusters. We're going to go ahead and drop these down. We want to look at, let's say, business. Let's look at a little bit of influence from education, because college degrees, a number of people with college degrees do make a difference. And then technology as well, obviously. And go ahead and apply those changes. And then we'll also change the node size and node color here. And that's more applicable for our use case. So we're going to start, let's look at IT, basically IT industry establishments, a number of companies. And then we'll color by college education. We'll come up here to the clusters up on the top left. Okay. So we get a rather large cluster up here at the top with I'm calling the heavy hitters of innovation. So obviously San Fran and Silicon Valley, Palo Alto area, Boston, which has a thriving community with Cambridge, or MIT and so forth at Cambridge, and then DC, New York rounding that out. But you may wonder, as I did when I first looked at these, why are Pittsburgh and Philadelphia, for instance, in this cluster? And it may be that they were misclassified or misgrouped, but I actually think there's something to this. Both Philadelphia and Pittsburgh, even though they're not thought of as innovation hubs, have pretty thriving cottage IT industries. So for Philadelphia in particular, with the drug industry on the East Coast, a lot of the pharmaceutical companies either have a presence in the Philadelphia area, or a lot of the people work there and commute up to other areas. And then also IT organizations or companies that build software for these companies tend to domicile in Philadelphia as well. So there's some intuitive explanation for that one. And Pittsburgh, with Carnegie Mellon there, has actually a pretty thriving, not huge, but a thriving startup community. There's Duolingo, which is a language, really nice language, learning to speak languages mobile app, is based out of Pittsburgh, as is the Visimo, which was recently acquired by IBM to become its Watson Explorer search engine. So that is one cluster that's sort of the heavy hitters, but there's a couple of other clusters worth noting, and these are down here, more towards the bottom here. Resize the screen, bring those up. I know it's a little jumpy on the web session. Here we go. Okay, so there's 2 clusters that I found interesting when exploring the data. So Oklahoma City, which is where Exaptive is based out of, rounds out a group with cities like Raleigh, Memphis, and St. Louis, Louisville, again. And that makes sense to me. So Raleigh, particularly with the Research Triangle and Cary, is a pretty burgeoning software space, even though people don't always think of that. You've got companies like SAS down there, SAS. So that is a reasonable cluster, and particularly what you see with a lot of those East Coast and mid-country smaller cities is they do a sort of a pull or a brain drain from the more expensive East Coast areas where you see firms moving their operations down to those areas because it's a good talent pool. So education, particularly in Raleigh, is pretty high, but it's a lot cheaper for cost of living. And you see something similar, in Memphis, you see it in Raleigh, you see it in Oklahoma City. This other cluster here is interesting to me, partly because it's my neighborhood. So Columbus, Indianapolis, Cincinnati are both all, a 2-hour drive of where I live, and I've spent a fair amount of time in Salt Lake and San Antonio. This I think of as sort of the defense industry cluster, as it were. So a lot of defense and financial institutions find their home sort of in the center of the country. There are bases in, obviously, Dayton, Salt Lake City, and San Antonio. So you see this kind of cluster forming, and again, that makes intuitive sense. So, again, I'm not going to predict where the next IT bubble occurs, but there are some interesting trends here of styles of city. So, for instance, if I were a betting man, I might pick up some real estate in one of these cities right here because this is where the growth appears to be happening. All right. So enough mulling that one through. All right, so I want to say thank you, and before we jump into questions, just say a quick thanks to a couple of folks on the Exaptive team that helped build some of what you saw today. So Mark Whistler helped with a lot of the machine learning componentry behind the scenes, and Derek Grape helped make this Frankenstein of an application I initially built look more like the Sistine Chapel. So thanks to both of them. And Bill, I'll turn it over to you to start Q&A.
Well, Matt, thanks for that excellent presentation. We'll get started with today's Q&A session, and I want to thank the audience for their participation. We've had a great many questions that have come in during the presentation, so we'll do our best to get through all of them in the time remaining. And during the Q&A session, I'll leave up this screen with contact information for Matt if you'd like to contact him following today's webinar. So let's get started. Matt, why did you choose Python as opposed to, say, R or other analytic languages?
Yeah, great question. That's the other quintessential choice. So we predominantly chose Python because of its a couple of things. Its ability to wrangle data easily. So as a bit of context, I've developed in C, C++, Java, Python, R, .NET, sort of you name it. So I've seen all the different languages and their pros and cons. And Python has always excelled, even 10, 15 years ago when it was used in the bioinformatics space, at its ability to pull in data and transform it and work with it in the fraction of the lines of code it takes to do something like that in another language like Java. So that's one predominant reason. R also has that ability once you sort of get it into the data frame format. The big reason we chose it is more for its available libraries. There's a host of algorithms that have been built into modules, whether it's scikit-learn, which is built on top of NumPy and SciPy, but also things like the Levenstein distance and the Tanimoto coefficient that actually have implementations in Python that we can grab off the shelf.
Great, thank you. And kind of an extension to that, a number of audience members are wondering why JSON as opposed to, say, something simple like CSV and then read into R?
Mm-hmm. Yeah, that's an excellent question. So a lot of the reason the appeal for JSON or for some of these other nested languages like XML is the ability to easily capture relationships without needing to do a lot of sort of binding and wrangling. So if you think of sort of how CSV or even just relational tables work, every time you would bring in a file, you would need to keep a key that somehow then bounded back to the higher level that you're interested in. So we have the hierarchy of cities, and then under that we've got observations or the metrics, and then under metrics we've got a series of observations, one per year. So it let us sort of capture all that in one concrete bundle. We tended to avoid XML because there's just a lot of writing and reading overhead, sort of the logic to create a well-formed XML document. when really what you care about is the internal structure. It is also very easy to navigate a JSON structure in Python and JavaScript or other languages.
Okay, thanks. Great answer. You know, obviously, we've been viewing this on the Exaptive platform. In what way did the Exaptive platform facilitate this analysis? And I presume the visualizations we're looking at, for example, are a product of Exaptive. What flexibility do you have to change those?
Sure. Yeah, that's a great question. There's a lot sort of wrapped up into that. On the algorithmic side, most of what you've seen here was built in Python, and that can run sort of command line, shell script, etc. So you don't have to be within a platform to run that. The advantage of bringing into a platform like Exaptive is then those components become reusable. So the next time you have a time series data you need to analyze with these steps, you don't have to go and grab a library from Python or go grab code and bring it in and sort of modify it. You can just bring it in as a component in the Exaptive platform as a development environment behind the scenes, and you can wire it up and go. So it's an accelerator from that perspective. Definitely the visualizations, though, like for me, who's more of a data guide, DBA, and data mining, being able to grab these visualizations off the shelf and use them is a huge time saver because I'm not gifted in the CSS land and such. So much of what you see here, from the sliders to the where you were able to color the nodes differently to the graph itself, are all components within Exaptive. And so being able to wire those together with the outputs of those algorithms is really where I've found it to be very beneficial.
Yep, that's really a powerful looking platform with those features. You know, from a strictly data science standpoint, obviously we have a lot of folks interested in, you know, how did you deal with, for example, missing data?
Mm-hmm. Yeah, that's a great question. So this was one we struggled with more for the other project, for the global health data, than this one. So the data from the census and from FBI was relatively dense, so most values were there with a few exceptions. In the global health data, it was very, very sparse. There would be just wide gaps both in what countries had data and when it was recorded. And so we really had to develop a robust missing data facility to do that. So the way we handled it was predominantly through how we developed a distance metric for the strings, the SAX features. We used that, the Levenstein distance, where it was looking at inserts and deletes and such, but we added an accommodation for if there was a missing value. It basically did not it did not compare it. It didn't factor into the distance calculation. And what was nice about that was it allowed us to avoid some of the pitfalls you can get into when you start extrapolating data. Interpolating is probably okay when you're missing a few data points along a smooth curve, but once you start trying to predict out into the future or back in the past, that becomes can be very problematic. So mostly how we handled it, and some of the other way is through these higher order features. As you extract more abstract features, you can handle some of this variability easier. You're not as prone to very sensitive lines. And again, that's honestly how our vision and other features of our nervous system work, where once we extract these features, it's why we can tell if it's an A when there's a portion obscured or when it's flipped upside down, because we're able to handle this variability with the higher order features. Okay,
makes sense. A lot of questions have come in regarding your selection of k-medioids as the clustering algorithm.
Yes.
Maybe you can just start by explaining why you picked that one as opposed to something either easier or more complex. And at the same time, let me add to that, for example, how does k-medioid handle the cluster numbers as features? Wouldn't the cluster number be arbitrarily chosen when the cluster is run?
Mm-hmm. Yep. So those are all good questions, and there's no one right answer I've found when it comes to clustering. So we chose sort of the k-means, k-medioids space for their simplicity and for honestly being able to visualize these types of things quickly and easily. We've looked at other clustering algorithms like hierarchical and DB-scan, which is some more of the density clusters. So we've looked at a variety of those in other scenarios as well. And honestly, from my perspective, and what would make this tool and one of our sort of future directions to make this tool more powerful is bring in multiple different clustering algorithms that people can experiment with and see how those differ. So that's another advantage of doing this in Exaptive is we can wire in a different clustering component and make that a drop-down and then have the clusters change based on the selection. And that could be a Python component. It could be something that you hand wrote. It could be using a clustering algorithm in R. So it does allow you to bring in these different types of languages to bind together in this common format.
Okay. All right. I can understand that. Question about in what sense this is time series data. Question from this viewer is, how is the time series historical aspect of the data reflected in the clusters? What if a city used to have a certain characteristic but now has significantly different characteristics?
Yeah, that's great. That's great. So that gets to the essence of why I think this approach is helpful, because the SAC string, that feature extraction will capture that shape. So it will treat a city differently if it's had a steady increasing curve versus one that had sort of a hockey stick curve later on. So it's not trying to judge whether one city is good or bad. It's basically saying what's its historical profile look like. And in doing that, you can look at cities that sort of follow a similar trajectory. Again, they don't have to be sort of lockstep year by year, but they follow a similar path. How many sort of substitutions do you need before you can match those two curves? And we have, so for that being said, we have looked at different ways, and you can weight, for instance, more recent values more heavily than older ones. That's one approach. You could have a cutoff and say, I only want to look at the last X number of years. So there's different ways that you could handle that. You could also look at how you calculate that frequency. Rather than taking an average, you could take the last 3 years average or something like that. So there's lots of different tricks you can do. It's why this is not so much a black box push a button as it is with all of those sort of dials and knobs on the right-hand side. And envision, just based on these questions, 3 or 4 additional things that you might want to add for a user to come in and tweak and play with.
Well, thanks for that explanation. So further to SACs, since many of us are not familiar with SACs, what data corresponds to a single character in SACs output? Is it one per time series, or one per measurement, or some third thing?
Sure, some third thing, and that's the annoying consulting answer of it depends. So it's a parameter so that you can pass it. So the way SACs works is you give it a window size, and that window size can be one character. So in this instance, every year became its own letter, or you can say 2, 3, 4, however many measurements, consolidate down to one letter.
Okay, all right. Third answer, yeah. Back to the visualizations, there was a question. Those clusters were very visually arresting and attractive, but how did the visualization pick the center point, the center city for those clusters?
Actually, the algorithm did. So the algorithm came out with a sort of determine what the centroid was based on the distances to all the cluster members, and so when the data headed into the visualization, it said, here's this is my center point, and here are the spokes, and then the visualization laid it out around that center point.
Okay.
And it arbitrarily picked. Yes, that's right. Yeah, and it arbitrarily picked the location on the canvas as to where any particular cluster would be positioned.
Great. Oh, I like those visualizations. That was very easy to follow, especially with the sliders. Would this approach work for city data as opposed to this level, or what other types of time series data would this approach work for?
Yeah, we found it works quite well for time series data that has some long trends. So it's not, as I mentioned before, it doesn't work as well, this particular feature extraction, for cyclical data. So if you were looking at financial markets, or you were looking at weather patterns or things like that, there's probably different initial features that you would extract, but then the remainder of the algorithm would work fine. But it works well for, so we've looked at things like growth data for children. There you need to normalize it versus sort of a standard growth curve. Since everybody's sort of going up, it just depends on whether they're growing per their expected age. So time series data, like growth curves, you mentioned cities, yes. So we're at the metro area. You could bring that down to an individual city. You could roll it up to states, which might be interesting if you were looking at funding or any kind of political aspects around states. You could see which states group together, things like that.
Okay, so those seem to be, if I understand your answer correctly, those seem to be fairly short-term predictive events. Is this actually a technique for predicting things about a city in the future?
Yeah, that's the million-dollar question. So yes, it can be with some extensions. So one of the things that you can do, and we've done this for other data sets, is you can basically time shift or time slice a particular city. So let's say we want to see what did Silicon Valley look like 10 years ago, right before, actually, I have to go back further than that, 20 years ago. You go back far enough and you say, what did it look like before the boom? And what were those characteristics? You can then compare what Silicon Valley was then with all the other cities in the country now and sort of say, what's potentially on the bubble? The other thing you can do is in terms of prediction, and this is, take it with a grain of salt, like it wouldn't be something that would be definitive. It's more of an area of exploration. But once you have a sense of what cities are similar, you can start extrapolating. Might be a little dangerous, but you can say, you know, if you do something in this city and it worked, is it more likely to work in this other city that's similar versus something that's completely different? Now, you wouldn't want to just take those answers blind and run with them, but you probably could take that as an early predictor to then do some additional, more rigorous statistical analysis on a particular area of interest.
Okay. Well, obviously the ability of this technique to predict is real interesting. A question from the audience, how granular can this project get? Could I say look at shopping trends for one particular week of the year using 15-minute sale intervals?
Yeah. Yes. Yeah, that's the other advantage of this kind of approach, is it's largely time scale agnostic. So absolutely, you can basically use the facts approximation on very granular data. You can extend that window a little bit. So let's say if you wanted to look at hourly data, you could take your 15-minute intervals and have a window of 4. But it absolutely could work. And we found it tends to work very well on either a lot of transactions or, in this case, you know, not many transactions, as there were not many cities, but a lot of metrics, right? 500, 17,000. You can really ramp up the number of characteristics that you look at simultaneously.
Well, it's interesting and exciting work, and an area that I hadn't personally explored. So, hey, thank you for that presentation and some great answers to some very good questions. For those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Matt and the Exaptive team so they can follow up with you after today's webinar. I have just a few quick announcements. If you would please mark your calendars for March 15th, which is our next Data Science Central webinar, which is how data can protect you from cognitive bias, and that'll be sponsored by Tableau. Also, remember that today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. And I'd like to thank our audience for their attendance and thoughtful questions. And a special thanks again to Exaptive for their sponsorship and our speaker today, Matt Coatney, for his insight into today's topic. My name is Bill Voorhees. I'm very pleased to have been your host for today's event. and I look forward to seeing you all again on March 15th. Have a great day.